Okay. Yes.
I'm also going to go over
Uh-huh.
these two because he really emphasized on these because I get confused.
Electrophilic air messages and NAS. Yeah, yeah. I will go over that as well for pyridine. Yeah, yeah.
Those three
Uh-huh. EAS and NAS on pyridine, right? The EAS and NAS reactions on the pyridine. Yeah, yeah. Yeah, yeah. I'll go over that too.
Thank you.
Yeah, uh-huh.
Also, are you Greek?
A bit.
Yeah.
Yeah, yeah, yeah. I am. Are you? Are you?
Oh, are you from born here or you from?
My parents were born in Vietnam. My dad was in like the north side. Oh no, no, south side. South side, and my mom is from the central side. But I was born here. Yeah, yeah. How about you?
I came from a country.
Oh, I see, I see. When did you move here?
Here, like during high school.
Oh, during high
Because I saw
school.
your name's John, so I was figured out, oh, you must
Yeah.
be me.
Yeah. What's your last name?
Boy.
Oh,
Your name is Yabao. Because
middle name. Middle name.
Oh,
Yeah, yeah,
yeah.
yeah. Oh, yeah. But my Vietnamese name is Yab Ao. Yeah, yeah,
Oh,
yeah.
Yabao.
That's my Vietnamese name. What the heck? Yeah. Okay.
Are you a senior?
Yes, I'm graduating this quarter. My last quarter here.
Congratulations.
Thank you. Thank you.
You're at school yet?
Uh, I'm going to chiropractic school right after this. Chiropractor school.
Chiropractic.
Yeah, yeah.
Congratulations.
Thank you. Thank you. Okay. 118C. So, chapter 25 is the heterocycle chapter, right? And there are three of the five-member rings that you have to know and be familiar with. There's the one with nitrogen. There's the one with oxygen. There's the one with sulfur. And you have to be familiar with the names of these, right? The one with the nitrogen, do you guys know the name of that? Pearl, oxygen, furan, sulfur, thiophene, right? So the ways to make this are going to be the Pau-Nor synthesis. I need a better eraser really quick. Pau-Nor synthesis. Um,
Can we move this?
move
Just like
this side.
we cannot.
Oh, yeah, 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 yeah. Sorry. Yeah, yeah. Pau-Nor synthesis. Okay. So this is gonna be a 1,4 dicarbonyl, right? If you react that with some kind of amine, RNH2, in acidic conditions, you're going to get the pyrrole, where the R group of the amine is the R group of the pyrrole. If you react that with P2O5, you're gonna get the furan. If you react that with P2S5, then you get the thiophene. Right? Yeah, the HCl is for the pyrrole, right? HCl is needed for the pyrrole because that's needed for the mechanism, which is a note card thing. 1,4 dicarbonyl is something like this, where we have a carbonyl that has a 1,4 relationship with each other. So we have 1, 2, 3, 1, 2, 3, 4, like that, right? And then if we number this like this, 1, 2, 3, okay, that's 1, 5. Uh, 1, 2, 3, 4, right? Then that's gonna be this 1, 2, 3, 4 right there. 1, 2, 3, 4. 1, 2, 3, 4. And you notice how at carbons 1 and 4, there's a methyl group right there. You would just have to put that methyl group right there, like whatever is attached to um, the carbons. Like let's say this was a isopropyl group on carbon 2, then you have to also include the isopropyl group on carbon 2 as well. Um, if you see this on the exam, it's more clear to see it in this form right here, right, where they are right next to each other like this, right? Where this is the exact same 1, 2, 3, 4 thing. It's just rotated and flipped, right? But you might see it like this on the predicted products, where you just think of it like this, rotate it in that form right there, right? So the next thing is, yeah, okay. So the EAS reactions on these things here. Picture? Good? Okay. So whenever you have any of those three reactions and you try to do EAS on them, like let's use Pearl for example. EAS reactions for aromatic rings are like bromination, halogenation, um, nitration, sulfonation, and the Friedel-Crafts reactions, right? Friedel-Crafts acylation, Friedel-Crafts alkylation. Um, let's do an example like bromination, Br2, Fe, Br3, right? I'm gonna say that these positions here are the exact same, so I'm gonna label that as A. These positions here are B, right? Because we have a plane of symmetry down the middle. So if we attach a group on A, it's the exact same thing as if we attach it on the other side because it's symmetrical, right? Do you guys know which position we prefer to attach the electrophile onto this parallel here? Right, so it's gonna be A, that's right. And do you know the reasoning why it's gonna be A? Yeah, more resonant structure, right? So let's look at the A case right here. When we put, and then the B case is gonna be right here. Right? This carbon here will lose a bond, giving that carbon a positive charge right there. We see that we could do resonance by moving this double bond down there to create this resonance structure here. Right? And then this pair of electrons on nitrogen can pop down to make the double bond and give that resonance structure here. So a lot of this stuff here is going to revisit 118A resonance. There's a lot of resonance in this chapter, right? And then that's the reasoning of a lot of these reactions, like why this happens. So we have a positive charge here. So that's it. That's all the resonance structures for A. Let's look at the case of B. Right? If we put a bromine on position B, carbocation there, we could pop that double bond down from that lone pair and get this resonance structure here. And that's when we stop the resonance structure, right? We see that at position A, we get three resonance structures. When we put the electrophile on position B, we get two resonance structures. So that makes A the major product, B the minor product, right? So whenever we do bromination on either parol, furan, or thiophene, always attach it to the carbon closest to the electronegative atom because of the resonance structure there. Right? Yeah. Okay, that's it. Indole. Okay. Uh-huh. Furan, thiophene, and pyrrole. Right. Um, think of it as the five-membered ring right here, where one of the atoms in the five-membered ring is an electronegative atom, either nitrogen, which is pyrrole, oxygen, which is furan, or sulfur, which is thiophene. Right. All of those will do react the same way because of this resonance structure here. Okay. Yeah. Okay. Let's go over indole now. So if we have indole, right, and then this will also be EAS reactions as well, right? Let's look at the EAS reaction of Friedel-Crafts acylation. Let's say we have this acyl group and then AlCO3, right? We could either attach it to position A or position B, right? So we do the exact same reasoning as like the last time we did. If we put it on A, let's see how many resonance structures we get, right? Right. We see this positive charge here can be resonance stabilized by this lone pair of electrons on nitrogen right there. So when I draw that resonance structure, this is what I get. Right? And then that's it. Let's look at the case of B. When I put the electrophile on carbon B, this is what I get. Right? We don't want to interfere with the benzene aromaticity here, so that's why we're not going to do resonance with the double bond right here, because that's going to break the aromatic ring. Same as for this case here, we don't want to interfere with the benzene ring, so this is where we stop. This lone pair right here cannot make a double bond with that carbocation because this carbon here is an sp3 roadblock for resonance. Right? No resonance. Because we have an sp3 atom in between the sp2 and the sp2 atom over here. Right? So in this case, we only have one resonance structure. In this case, we have two. So A is the major one where we put the electrophile on this carbon here. Okay. Hunt synthesis. Okay, let's do a conceptual thing with acid and bases and hybridization. Right. Okay. Yeah. The more reactive ones would actually be the ones on the heteroatom because think of it as this is an EDG right here that activates this ring better than the benzene ring here. Like this ring has a pair of electrons that activates the whole ring, making it more nucleophilic than the benzene ring here. Right? Yeah. Yeah. Uh-huh. So I'm gonna give you two structures. Um, right? Let's say we have this pyridine and this pyrrole here. Which one of these nitrogen atoms is more basic? More basic. Right, the left one because so there's no hydrogen on this nitrogen here, so we can't say where's acid. The best way to explain this is that the lone pair on that nitrogen here is less stable than the lone pair on this electrons here, right? Can this pair of electrons do resonance? No, right. This goes back to 118A. When the pair of electrons is on an atom that is already double bonded, right? That double bond is already occupying the p orbitals of that nitrogen and that atom that's double bonded with it, right? That makes this pair of electrons here in an sp2 orbital, right? That cannot do resonance, right? Whereas this pair of electrons here, is this atom double bonded to anything? No, right? So this pair of electrons here is actually in a p orbital that can do resonance, right? With all of these other p orbitals here, because we could like just do that, go all around, right? This pair of electrons here is stuck and localized, making this pair of electrons less stable and this pair of electrons more stable. And if a pair of electrons is less stable, it is more reactive or more basic. If this is more stable, this is less reactive because it's more stable, making it less basic. It doesn't want to react with anything because it is already stable and happy by itself. Right? So this could show up as an acid-base question, ranking question, like which is the most acidic or basic atom. Right? But you have to look at the stability of the pair of electrons. The more stable it is from resonance, the less reactive it is, the less basic it is. Right? I mean, the less stable it is, the more reactive it is, the more basic it is, right? Yeah.
That was a question asking which was the strongest acid.
Strongest acid.
Like I understand how you could explain it for the pyrrole.
Yeah.
Because like once it gets deprotonated, it can do resonance.
Yeah, it can do
But, like, how
resonance.
would you explain it for the pyridine?
So for the pyridine here, there's no like very acidic hydrogen because there's no hydrogen here on that nitrogen. The only hydrogens we have are these carbons right here. And when we deprotonate these carbons, the negative charge here cannot do resonance, right? Whereas the negative charge here can do resonance, and it's part of the aromatic ring, making that very stable. Conjugate base, very acidic hydrogen here. Yeah. Right. Okay. Okay. Next thing is the Hans synthesis, but I didn't see this on his practice final, so I don't know if he was gonna put this on the final. But let's just go over it just in case. It has a lot of moving parts to it. Okay. So Hans synthesis. Right. So for this reaction, you are gonna have two. Hmm, 1,3 dicarbonyls, where one carbonyl is gonna be an ester, the other carbonyl is gonna be a ketone. You're gonna have one either ammonia or primary amine. You're going to have one aldehyde. Right? So if you see these on your reagents or reactants, um, this is the template of what you do here, right? Like let's say we have that. Yeah, it could be R2NH2 or
So we need to see all of these in reactants.
yeah, all of these four reactants here for synthesis. Two 1,3 dicarbonyls, one aldehyde, and one primary or ammonia amine.
I'm sorry, I don't catch it. Can you explain this? Like these three, they are involved in the hands.
Yeah, these three things here are involved in the Hans synthesis. But for this one here, we need two of them, which are these two here. 1, 2, right? This is the 1,3 dicarbonyl because when we do 1, 2, 3, that's a 1,3 dicarbonyl. Where one of it is an ester, which is this ester here. The other one is a ketone, which is that ketone right there.
Yeah.
Right. So here's like the template of like how you predict the product here. Right. Where we're gonna I'm gonna draw out the end as like this actually. No, no. It's if it stops again, then I'll just like not record. Yeah. Thank you for letting me know. So, right, HNO3, H2SO4. You notice how this is not an aromatic ring? We could further do a reaction that would aromatize that ring using HNO3 and H2SO4. Right?
Wait,
Yeah.
why can't like the bone pair on the nitrogen come in and make it?
This lone pair of the nitrogen here can do resonance with the two carbonyls here,
So
but
isn't that aromatic?
to be considered, it has to be fully conjugated.
Oh, but that's complex.
Yeah, this carbon is sp3, right? It's not fully conjugated. This reaction here will make it all aromatic. Yeah, which is gonna be this aromatic ring right here, right? Now, what do you guys notice about these two esters here? What is the relationship between those two esters? Yep, they're the same esters. But like let's look at this carbonyl here. What is this carbon relative to that carbonyl? Is it alpha, beta, gamma, delta, epsilon?
Is it one?
Oh yeah, it is gamma. It is gamma. 1, 2, 3. Yeah. So this is not 1, 3. This is 1, 2, 3, 4, 5.